Two identical spacecraft, one mission, two completely different destinies. Voyager 1 is faster, Voyager 1 is farther. Voyager 1 gets the headlines. But there's one thing Voyager 1 never did, never could do, and never will do. Voyager 2 flew past Uranus and Neptune, the only spacecraft in human history to visit either planet ever. Not once has another probe been sent back. For almost 40 years, that flyby was treated as settled science, filed away as one of the strangest results in the solar system. Uranus, they said, had the most extreme, most chaotic magnetic field of any planet we'd ever measured. A cosmic outlier, broken, backwards, different from everything else. Then, in November 2024, a team led by NASA Jet Propulsion Laboratory scientist Jamie Jasinski went back into that old 1986 data with modern tools. And what they found didn't just add a footnote. It rewrote the story of what Voyager 2 actually saw. The broken planet might not be broken at all. The mission may have arrived during a 5-day window that was, statistically, almost the worst possible moment to look. And for 40 years, we built our entire understanding of an ice giant on that single unlucky snapshot. This is the story of the spacecraft that went where its twin never could, and the discovery that just quietly rewrote what we thought we knew about our own solar system. To understand why this matters, you have to go back to the 1960s, to a coincidence of celestial mechanics that happens roughly once every 175 years. NASA scientists realized that in the late 1970s, Jupiter, Saturn, Uranus, and Neptune would align in a way that let a single spacecraft use each planet's gravity to slingshot toward the next. A free ride across the outer solar system that would otherwise take decades and multiple missions to achieve. 2 spacecraft were built to take advantage of it. Voyager 1 and Voyager 2 both launched in the late summer of 1977, both carrying the now famous Golden Record, a phonograph disc of sounds, music, and images meant to explain who we are in case anything out there ever finds it. Voyager 1's job was speed and specific targets, Jupiter, Saturn, and Saturn's giant moon Titan closely enough that it had to bend its own trajectory up and out of the plane of the solar system to do it. That decision effectively ended Voyager 1's planetary tour. It would never see Uranus or Neptune. It simply wasn't on the flight path anymore. Voyager 2 took the long way. It kept to the plane of the planets, and because that rare planetary alignment held together, it could keep going. After Jupiter and Saturn, it kept its engines pointed at 2 more targets nobody had ever seen up close, Uranus in 1986 and Neptune in 1989. To this day, no other spacecraft, not one, from any space agency on Earth, has been sent to either planet. Everything humanity knows about Uranus and Neptune from direct observation, we know because of 5 days at Uranus and about 2 days at Neptune, flown by a machine built with 1970s computing power. That's worth sitting with for a second. Every textbook image of Uranus's tilted rings, every diagram of Neptune's storms, every measurement of their magnetic fields, it all traces back to one brief pass, decades ago, that we've never been able to repeat or verify. Both Voyager spacecraft carry a suite of instruments that sound modest by modern standards. Magnetometers, plasma detectors, cosmic ray sensors, cameras with far less resolution than an ordinary smartphone, running on computers with a tiny fraction of the processing power most people carry in their pocket today. And yet those instruments, built by engineering teams working with slide rules and early digital computing, are still the only direct in situ measurements humanity has ever taken of 2 entire planets. Every robotic mission since, every Mars rover, every Jupiter orbiter, every mission to a comet or asteroid has had the benefit of decades of accumulated spaceflight experience that the Voyager program itself helped create. Uranus and Neptune never got that benefit. They got one shot decades ago and nothing since. On January 24th, 1986, Voyager 2 made its closest approach to Uranus, coming within about 500 kilometers of the planet's cloud tops. In less than a single day of close-range science, it discovered 10 new moons and 2 new rings, and captured the only close-up images of Uranus's 5 major moons that exist to this day. But the biggest surprise wasn't the moons or the rings, it was the magnetic field. Every other planet we'd measured, Earth, Jupiter, Saturn, has a magnetic field that's roughly aligned with its spin axis, like a bar magnet tilted only a little from the poles. Uranus's magnetic field was tilted about 60 degrees off its rotational axis, and it wasn't even centered on the planet. It was offset, lopsided, strange. On top of that, Voyager 2's instruments found something that seemed even harder to explain. Intense, energetic radiation belts around the planet among the most powerful measured anywhere in the solar system, second only to Jupiter's, but almost no plasma. The space around Uranus looked, in the data, essentially empty of the charged particles you'd expect a planet's moons to be shedding into their environment. That combination puzzled scientists for decades. If the radiation belts were so intense, where was the plasma coming from to feed them? And if Uranus's 5 major moons were as icy and potentially active as models suggested, Why did space around them look so empty? For a long time, the simplest explanation scientists reached for was that Uranus itself was just fundamentally different. A colder, quieter, less geologically active world than its neighbors, with moons that were essentially dead ice balls doing nothing. Uranus became the outlier of the outer solar system, the weird middle child nobody could quite explain, and Uranus wasn't even the last stop. 3 years later, on August 25, 1989, Voyager 2 made its closest approach to Neptune, coming within about 4,150 kilometers of the planet's cloud tops, the closest any spacecraft has ever flown to any planet during a flyby mission. In that single pass, it found 6 new moons, confirmed and mapped Neptune's faint ring system, and captured images of the Great Dark Spot, a storm system roughly the size of Earth churning in Neptune's atmosphere, one that later observations from the Hubble Space Telescope showed had actually vanished by the mid-1990s, only for a new dark storm to appear elsewhere on the planet years later. Neptune's magnetic field turned out to be tilted and offset too, in a way that echoed what Voyager 2 had already seen at Uranus, which at the time seemed to confirm that ice giants really were fundamentally different from gas giants like Jupiter and Saturn. Voyager 2 also gave humanity its only close look at Neptune's largest moon, Triton, a bizarre, backwards orbiting world with a surface of frozen nitrogen and active geysers venting nitrogen gas in dark dust kilometers into its thin atmosphere, some of the only confirmed active geological venting found on any moon in the outer solar system at the time. Scientists still debate whether Triton is a captured Kuiper Belt object rather than a moon that formed alongside Neptune, and every theory about it still traces back to the same few days of Voyager 2 images from 1989. No mission has been back since. Nothing is currently on its way. That's the pattern running underneath this entire story. 2 ice giants, 2 singular flybys, decades apart from any possibility of a follow-up, and in both cases, one shared conclusion. Uranus and Neptune looked strange, tilted, and unlike anything else in the solar system. For nearly 40 years, that conclusion held. Then someone finally went back and asked whether the data itself might have been the problem, not the planet. Here's where the story leaves 1986 and jumps to now. In a paper published in Nature Astronomy in November 2024, Jashinsky and a team of co-authors from JPL, the University of Michigan, University College London, the Max Planck Institute for Solar System Research, and Johns Hopkins Applied Physics Laboratory went back and did something nobody had really done before. They looked closely at what the solar wind, the constant stream of charged particles flowing outward from the sun, was doing in the days immediately before Voyager 2 arrived at Uranus, not just in the hours right around the flyby itself. What they found was that in the 2 weeks leading up to the encounter, the solar wind pressure hitting Uranus was unusually low. Then, just days before Voyager 2 arrived, it spiked, sharply. The researchers estimated that the dynamic pressure of the solar wind at the moment of the flyby was dramatically higher than normal, compressing Uranus's magnetosphere down to a fraction of its typical size. Their modeling suggests this kind of extreme compression happens less than 5% of the time. Voyager 2 flew through Uranus's environment during a rare squeeze, and only had that one 5-day window to look. Think about what that means. If Voyager 2 had arrived even a week earlier, before that solar wind spike, the upstream pressure would have been roughly 20 times lower, and researchers now believe Uranus's magnetosphere would have looked dramatically different, probably closer to what we'd expect from a more ordinary ice giant. The empty-looking plasma environment? The new analysis suggests the incoming solar wind event likely compressed the magnetosphere and pushed plasma out of it, not that the system was naturally empty. And the unusually intense radiation belts that puzzled scientists for so long may be a temporary side effect of that same compression event, not a permanent feature of the planet. That has a real, tangible follow-on implication. If the missing plasma around Uranus's moons was simply blown away by a passing solar event rather than reflecting a genuinely inert environment, it reopens a question that had been treated as basically closed. Whether Uranus's icy moons, like Ariel, Miranda, Titania, Oberon, and Umbriel, could be more geologically active than the dead picture we'd settled on. We're talking about a possible reconsideration of whether those moons vent material into space the way some of Saturn's and Jupiter's moons famously do. In other words, the single most defining data set we have about an entire planet may have captured that planet on one of its least representative days in the whole 1986 window scientists had access to. Everything downstream of that, the models, the comparisons to Jupiter and Saturn, the assumptions about the moons, has been sitting on a foundation the researchers themselves describe as likely skewed by a rare, short-lived event. Uranus isn't necessarily the solar system's broken outlier. It might just be a planet we photographed during a bad week. Uranus wasn't the last time Voyager 2 did something its twin couldn't quite match. On November 5th, 2018, Voyager 2 became the second human-made object ever to leave the heliosphere. the vast bubble of solar wind and magnetic field that the sun blows around itself, and enter interstellar space. Voyager 1 got there first, back in 2012, but Voyager 2 arrived carrying something its twin didn't have anymore, a working plasma science instrument. Voyager 1's equivalent instrument had failed years before it crossed the boundary, which meant scientists had to infer its interstellar crossing indirectly from other data. Voyager 2's plasma instrument was still alive, and it let researchers directly, unambiguously measure the moment the spacecraft passed from hot, sparse solar plasma into colder, denser interstellar plasma. That direct measurement mattered. Multiple papers published in Nature Astronomy based on Voyager 2's crossing showed that the edge of the heliosphere isn't a slow, gradual fade, the way many scientists had pictured it. It's a real boundary, thin, distinct, more like crossing a membrane than drifting through a haze. And Voyager 2's instruments captured something Voyager 1 could only be inferred to show: how the sun's own magnetic field, still attached to the solar wind, actually drapes around the outside of that boundary, while the interstellar magnetic field beyond it points in a different direction, creating a more complicated, layered interface between our solar system and the galaxy than the simple bubble most people picture. Between the two spacecraft, we now have two separate crossing events at different locations and years apart, both confirming that the heliosphere has a genuine, structured edge, not a smear. That's the kind of result you can only get by having two independent spacecraft cross the same kind of boundary in different places, which is exactly what Voyager 1 and Voyager 2 together uniquely gave us. There's an eerie side effect of that crossing, too, one that Voyager 1 stumbled into first. In late 2020, mission scientists reported that Voyager 1's plasma wave instrument had picked up a faint, continuous hum, a steady, low-level vibration moving through the thin interstellar plasma, distinct from the more dramatic bursts of activity triggered by solar eruptions. Researchers described it as something closer to a constant background tone than a signal, evidence that even the empty space between stars carries a persistent, measurable resonance once you have an instrument sensitive enough and patient enough to sit there and listen. Voyager 2's own plasma instruments have picked up similar activity in the years since, giving scientists two independent listening posts on what interstellar space actually sounds like, electromagnetically, rather than relying on a single spacecraft's account of it. That detail matters for the bigger picture of what these two missions represent. Voyager 1 crossed first, but without a working plasma instrument, meaning scientists had to reconstruct exactly when and how it happened, using indirect evidence almost after the fact. Voyager 2 crossed 6 years later, but with its plasma instrument still fully functional, so researchers watched the transition happen essentially in real time, plasma density rising as the spacecraft moved from the searing, sparse solar wind into the colder, denser interstellar medium. Together, the two missions did what neither could have done alone. They gave scientists both a live, instrumented account of the crossing and a second independent location to confirm the boundary wasn't a one-off fluke of geometry. For all its scientific value, Voyager 2 nearly went silent for good. Not from age, not from power failure, but from a single wrong command sent from Earth. On July 21st, 2023, a routine series of planned commands was sent up to Voyager 2. Something in that sequence caused the spacecraft's high-gain antenna, its only real link to Earth across more than 3 billion miles, to tilt 2 degrees away from where it needed to point. 2 degrees. At that distance, 2 degrees was enough to sever communication completely. Voyager 2 could no longer receive commands from mission control, and it could no longer transmit data back. It was, in practical terms, deaf and mute, still flying, still functioning, but cut off from the only humans who'd ever spoken to it. Mission engineers at NASA's Jet Propulsion Laboratory had a fallback. Voyager 2 is programmed to automatically reset its orientation several times a year to keep its antenna pointed at Earth as a safeguard, and the next scheduled reset wasn't due until mid-October, nearly 3 months away. Rather than simply wait, the Deep Space Network team in Canberra, Australia, tried something more aggressive. On August 2nd, they aimed the most powerful transmitter available and sent what engineers described as an interstellar shout, a high-power signal blasted toward Voyager 2's last known position, instructing it to reorient itself back toward Earth. Because of the distance, that command took over 18 hours just to arrive. Then engineers had to wait again for a response to travel back. In total, it took about 37 hours after the shout was sent before anyone on Earth knew whether it had worked. It worked. On August 4th, 2023, at 12:29 a.m. Eastern Time, Voyager 2 began streaming telemetry and science data again, operating normally, still exactly on its expected trajectory. Voyager project manager Suzanne Dodd later described the relief of that moment simply, that after weeks of tension, the team could finally exhale. It stands as the longest communication blackout in Voyager 2's history, and a reminder that even after nearly 50 years of flawless operation, this mission is still one small human error away from silence, permanently, with no way to send a repair crew. Voyager 2 runs on a radioisotope thermoelectric generator, essentially a chunk of decaying plutonium that converts heat into electricity. That power source has been quietly weakening every single year since launch, and there is no way to refuel it. Engineers have spent years managing that decline by strategically shutting down non-essential systems and instruments to stretch the mission's life for as long as physically possible, turning off heaters, cycling down instruments that are no longer critical, doing everything they can to keep the ones that matter most, like the plasma and magnetic field instruments, alive longer. There's no fixed shutdown date. Instead, there's a slow negotiation between engineers and physics, instrument by instrument, watt by watt, a process that has already stretched well past every early estimate for how long the mission could plausibly last. Voyager project scientists have described the approach in blunt terms. As long as there are even a few watts of power left, they'll keep trying to measure something. Some low-power instruments, like the magnetometer, are expected to be able to run longer than the more power-hungry ones. That mindset, measure something for as long as anything can be measured, is why Voyager 2 is still returning genuinely new science, decades past its original 5-year planetary mission. It's also why every year the spacecraft survives now counts as bonus time nobody can guarantee will continue. In 2023, engineers found an extra reserve of margin they hadn't planned on using. A small backup power supply, originally set aside as a safety buffer for onboard voltage regulation, was reallocated to keep science instruments running instead. A move, mission managers said, could extend Voyager 2's science-gathering capability by potentially several more years, compared to the original power-down schedule. It's a reminder that a lot of what's kept these two spacecraft alive this long isn't just the original 1970s engineering. It's decades of small, careful human decisions made from hundreds of millions of kilometers away, squeezing a little more life out of hardware nobody expected to still be running in the 2020s at all. Meanwhile, the two Voyagers aren't alone in that data collection anymore. NASA and other missions have continued watching the edge of our solar system in different ways. From IBEX, a mission that's mapped the heliosphere's boundary from Earth orbit for well over a decade, to the newer Interstellar Mapping and Acceleration Probe, IMAP, which launched in 2025 specifically to build a higher resolution picture of exactly the kind of boundary Voyager 2 crossed by accident. At one point in time, decades after its instruments were designed, Voyager 2 is no longer the only tool for this job. But it's still the only spacecraft that's actually been there, out past the edge, sending data back in real time from inside the boundary itself. It's easy to hear scientists reanalyze 1986 data and assume this is a minor footnote. It isn't. Here's why. For nearly 40 years, Uranus has been used as a kind of scientific baseline, a reference point for what an extreme, unusual planetary magnetosphere looks like, cited in textbooks, comparative planetology papers, and mission planning documents for future ice giant missions. If that baseline was captured during an atypical 5-day window rather than representative conditions, then a huge amount of downstream science, models of how Uranus's radiation belts form, assumptions about whether its moons are geologically dead, comparisons used to plan hypothetical future missions to Uranus or Neptune, may need to be revisited. And there's a sobering practical lesson buried in this too. We built decades of scientific consensus on a single data point, gathered during a single flyby, because it was the only data point we had. Nobody chose that limitation. It's simply the reality of exploring a planet nearly 3 billion kilometers from Earth, with one spacecraft, once, for 5 days, using instruments designed in the 1970s. There's no way to go back and try again with better timing. The only reason we even know the original data might be skewed is because researchers went back with modern solar wind models and re-examined records that had been sitting untouched for almost 4 decades. That's also, quietly, one of the best arguments for actually sending something back to Uranus. NASA's Decadal Survey for Planetary Science has named a dedicated Uranus orbiter and probe mission as a top priority for the coming years. Not because Uranus is exotic or alien adjacent in the way headlines love to frame distant worlds, but because right now, our entire scientific understanding of an entire class of planet, ice giants, which appear to be one of the most common types of planet across the galaxy based on exoplanet surveys, rests on data from one brief, possibly unrepresentative pass. That last point is bigger than it sounds. Exoplanet surveys from missions like Kepler and TESS have found that Neptune-sized and sub-Neptune-sized worlds are among the most common planet types discovered orbiting other stars, arguably more common than anything resembling Earth or Jupiter. Which means Uranus and Neptune aren't just two odd planets sitting at the edge of our own solar system. They may be our only close-up reference points for understanding an entire category of world that appears to be scattered throughout the galaxy in enormous numbers. If our one data set on that category of planet was gathered under unusual conditions, the ripple effects extend well past our own solar system, into how scientists interpret data from planets we'll never be able to fly a spacecraft to at all. A dedicated Uranus mission, if funded and launched in the coming years, Likely wouldn't arrive until sometime in the late 2030s or 2040s, given the multi-year travel time involved. Which means, for at least another decade, quite possibly two, the 2024 reanalysis of Voyager 2's old data is likely to remain the most current, most accurate picture of Uranus's magnetosphere that scientists have. Not new data, a better read of the old data. That's the situation planetary science is actually in right now, whether or not it makes headlines. Strip away the science fiction instinct to want aliens, conspiracies, or hidden messages, and what's left is arguably more impressive. A machine engineers designed using slide rules and 1970s computer chips, launched before most of the crew now managing it were even born, is still returning usable scientific data from beyond the edge of the solar system, still occasionally forcing us to rewrite what we thought we understood about a planet nobody has visited in almost 40 years, and still capable of nearly going silent forever over 2-degree antenna error, and still coming back from it. Voyager 1 will likely always hold the record for distance, for being first into interstellar space, for firsts that matter to history. But Voyager 2 did something its twin structurally cannot claim. It is the only spacecraft that has ever given humanity a close-up look at Uranus and Neptune, and it did it once, briefly, under conditions that, as of November 2024, we now know were probably not typical at all. Every image of Uranus you've ever seen, every diagram of its magnetic field, every assumption about whether its moons are alive or dead inside, all of it traces back to 5 days in January 1986, flown by a spacecraft that's been quietly rewriting the story of what it actually saw ever since. And it isn't finished. As long as there's power left to run an instrument, engineers at JPL have made clear they intend to keep listening. 2 identical machines, launched weeks apart in 1977, ended up writing 2 completely different chapters of human history. One became the fastest, farthest thing we've ever built. The other became the only eyewitness account we will have of 2 entire planets for the foreseeable future, and just handed us a reminder that even settled science can be one reanalysis away from a rewrite. So here's the actual question worth sitting with. If a single 5-day flyby, examined more carefully almost 40 years later, could change our entire picture of Uranus, what else is sitting in old data, in old missions and old assumptions, just waiting for someone to look again? Old spacecraft tapes, old survey plates, old readings dismissed at the time as noise or error. All of it sitting in archives, waiting for the right combination of curiosity and better tools to come back and ask the same question this team just asked: what if we didn't misread the planet? What if we just caught it on a bad day? If you want to go deeper, the 2 key studies behind this video are the November 2024 Nature Astronomy paper, led by Jamie Jasinski and colleagues on the anomalous state of Uranus's magnetosphere, and NASA JPL's own public write-up of that same research, both linked in the description, so you can read the primary data yourself instead of taking anyone's word for it, mine included. If this kind of deep dive breakdown is what you come here for, subscribe, because there's a lot more sitting in the Voyager archives that hasn't been fully re-examined yet. And if history is any guide, it won't stay quiet for long. Somewhere in a data center, on a hard drive nobody has opened in years, there's probably another settled result waiting for the same treatment Uranus just got.